So I'm going to divide this lecture worksheet number 6 and this new chapter in two videos. So at first, I'm going to go over question number 1, 2, and 3. So namely, I'm going to go over Faraday's Law, Lenz's Law, and the self-induced EMF. And I'll do the equivalent theory for each of these parts. And then I'm going to make a separate video where I'm going to focus on RL circuits and complete questions 4 and questions 5. So I talked a little bit about induced voltages and inductance previously. And if you remember, I gave a hint about Faraday that Faraday demonstrated that a current can be produced by a changing magnetic field. And this is an experiment we would have done in lab where we would have had coils and then we would have had a primary coil and a secondary coil. In this diagram, I have a primary circuit and a secondary circuit. So on the left-hand side, I'm going to write primary. And then on the right-hand side, I'm going to write secondary. And on the left-hand side, you can think of a battery or a electron pump. And we have a switch where we can close the circuit or open the circuit. And here in the middle, we have iron. And on the secondary current, in the secondary circuit, we have a ammeter, which will measure the current through this second circuit if you have a changing magnetic field. Okay, so this is an experiment we would have done in lab where we have a primary circuit, secondary circuit. Note that the secondary circuit does not have a battery, and we will get a reading of current regardless of not having a battery. Okay, so let's start really quickly by a definition. So then we can start question number 1, which is the magnetic flux. So an induced EMF, which is the electromotive force, we can think of, again, the unit of a voltage, is produced in the secondary coil or circuit by the changing magnetic field. So if we would have two coils or circuits, then by having a changing magnetic field, you will produce a current. Now let's take a step back and let's define the magnetic flux. We did this very briefly in our first lecture worksheet at the beginning of the semester. So I'm going to redefine now the magnetic flux. Okay, and we're going to use the flux sub B to note the magnetic flux. And the magnetic flux is proportional to the strength of the magnetic field passing through a plane of the loop, okay, or in a loop, or in a closed area. So here I have the magnetic flux will be equal to B perpendicular times A. And let me scroll down a little bit. We can look at this diagram and we can see that I have my surface area here, A, which in this scenario can be length times height, for example. And the B perpendicular component is nothing more than, or we can define as B perpendicular to be equal to the magnetic field, so B cosine of an angle. And here we have this angle theta, okay, between the red B perpendicular and this blue vector of B. And in this way, we can find the B perpendicular in this equation. So we can simplify, or we can plug B into our equation of magnetic flux, and we will have a equation where the magnetic flux is equal to BA cosine theta. I'm going to put a box here. Okay, and a very useful question when you are introduced an equation is to see, well, what is the upper bound or the lower bound of this equation? In our sense, we have a cosine theta in the equation, so we can think, well, what is the maximum, or what is B maximum? Okay, what is the maximum value? And the maximum value is when theta is equal to 0 degrees. Because here, when theta is equal to 0 degrees, then think of where this red line and this blue line will be one on top of the other. Okay, there will be no difference. So the B perpendicular to the surface is the magnetic field going through the surface. And in that case, if I have an angle theta to be equal to 0, then I have the maximum magnetic flux to be equal to BA. Okay? All right, so let's start the very first question in this worksheet, which will start us or lead us into calculating a change of flux that will be useful to then introduce Faraday and Lenz's laws. So the first question in lecture worksheet 6 is conducting circular loop of radius 0.250 meters is placed in the XY plane in a uniform magnetic field of 0.360 Tesla that points in the positive z direction, the same direction as the normal plane. So we have a physical dimension of 0.250 meters. We have a magnetic field of 0.360 Tesla, and we have a direction of this magnetic field. So we want to solve first the magnetic flux through the loop. Okay, now this would be quite simple, mostly plug and chug. So the first thing I'll do is I'm going to solve for the area of this loop. So the area is pi r squared. So with the information that we have pi multiplied by 0.250 meters quantity squared, which is equal to 0.196 meters quantity squared. So now I can solve for the flux. So I have the magnetic flux is B A cosine theta. So here I have my value of the magnetic field is 0.360 Tesla multiplied by A. So I have 0.196 meters squared multiplied by cosine of my angle. So in this case, the magnetic field is pointing in the same direction as the normal. So we have our angle theta to be 0, and therefore cosine of 0, which is simply 1. So I have the magnetic flux, which will be a value of 0.0706 Tesla meter squared, which is equal to 0.0706 Webers. Same value. I am writing the same value in terms of Tesla meter squared or Weber. So therefore, if I introduce a Weber or a Tesla meter squared, we feel a little bit more comfortable that they are equivalent. Okay, so let's then change the orientation of this loop. So part B states, suppose the loop is rotated clockwise around the x-axis, so the normal direction now points at a 45-degree angle with respect to the z-axis. Recalculate the magnetic flux through this loop. So we're calculating the flux again, and the only variable that is changing in this case will be this angle theta. So I can write the same equation as the magnetic flux is BA cosine theta. I'm going to write it underneath to have a bit more space. So the magnetic field is still 0.360 Tesla. I have my area to be 0.196 meters squared. And now we have the magnetic field at an angle of 45 degrees to the plane. And I can just plug in the values and see. So when I plug in the values, I will have 0.0499 Webers or Tesla meter squared. Remember that it's the same unit. Okay, so C is asking what is the change in flux due to the rotation of the loop? So this question is starting to help us get into the direction of a change of flux. So in short, we want to solve for the change of magnetic flux. And we know that the change of magnetic flux will be the flux final, I'll just write word final, minus the magnetic flux initial. Okay, so the last value we got minus the initial value. So it will be 0.0499 Weber minus 0.0706 Weber. And the solution is negative 0.0207 Webers. So this is the value of the change in magnetic flux due to the rotation of the loop. So now we are a little bit more acquainted with this magnetic flux, and we have a bit more of a manipulation on how to calculate different parts of this magnetic flux. All right, so let's introduce Faraday's laws of induction. Again, it is a little bit unfortunate that I cannot show this directly in the lab, but Faraday's law of induction is that if you have a loop of wire, or you can have a coil, and imagine you can have n turns. So you can just have a loop on rolled on itself n times, and you connect this loop to an ammeter. Okay, so remember ammeters will be connected in series. So you connect this loop to an ammeter, and then you have a magnet. So you can have, here we have a north pole, and again we have a south pole. Remember, field lines leaving one pole, entering the other pole. And in this case, we're going to have two directions of motion. We're going to first make this magnet go towards the loop, and then we'll keep the magnet stationary, and then we're going to move this magnet away from the loop. So if the magnet is moved towards the loop, we're going to have an ammeter, and the ammeter is going to read a current. When the magnet is stationary, there will be a reading of 0. So no current will be going through this loop. And when the magnet is moved the opposite direction, so if the magnet first moved from right to left, when the magnet goes from left to right, then the ammeter is going to also read a current. But this current will be in opposite direction. And it's an opposite direction to the first reading. Okay, so let's calculate the average EMF induced in the circuit. All right, so the average EMF, again, think of the unit voltage, induced in the circuit will be given by this following equation. So we have negative N remember that n will be the number of loops, multiplied by the change of the magnetic flux divided by the change of time. So here we have the change of flux divided by change of time. We can put a box here because we're going to use this a few times. And with this equation, we can solve for directly the EMF, or we can solve for the magnetic flux, or also maybe a change of time, and so on. And this negative sign, okay, this is the polarity, which is going to determine the direction of induced EMF. So this will determine direction of induced EMF. All right, so let me introduce Lenz's law so we can start question number 2. We're going to mix Faraday and Lenz together. So for Lenz's law, I wrote a few points that I'm going to read now, and then we're going to do the question, and I'll go back, which will make a bit more sense when we go over this twice. So first we have a current that is caused by the induced EMF travels in the direction that creates a magnetic field with flux opposing the change in the original flux to the current. Okay. Again, so there will be a current that caused by the induced EMF, and this current will travel in the direction that creates the magnetic field with a opposing flux. Okay, think of like a reaction, the change in the original flux. And then another explanation that we'll introduce in the example is that if the magnetic flux through a loop is becoming more positive, in other words, the value becomes a positive change of flux, increases, then the induced EMF creates a current and an associated magnetic field that produces negative magnetic flux. So it will go in the opposite direction. So I'm going to start the question number 2, and then I'll go back when the question will ask us with particular directions and positive or negative values. All right, so question number 2 is relating a question with Faraday and Lenz's. So we have a coil with 25 turns of wire that is wrapped on a frame with a square cross-section of 1.80 centimeters on each side, and a total resistance of the coil of 0.350 ohms. There is an applied uniform magnetic field perpendicular to the plane of the coil. This is there to give us the direction. So first, we want to find the changes. So when the field changes uniformly from 0 Tesla to 0.5 Tesla in a given time of 0.8 seconds, what is the induced EMF in the coil while the field is changing? So it's straight plug and chug. And in this drawing, I'm going to first solve for the area. So let's get some imagination and assume that here the lengths are the same. So each length will be 0.0180 meters. This will be L, this is also L. So the area is L squared, which is equal to 0.0180 meters quantity squared. So the area is 3.24 times 10 to the negative 4 meters squared. I'm going to underline this as we're going to use this number. All right, so to find the induced EMF, I'm going to first solve for the change of flux and then I'm going to plug the change of flux in the equation presented previously. So I have the magnetic flux final, okay, I'll start with the final first, which is BA cosine theta. So I have a magnetic field of 0.5 Tesla multiplied by the area I just solved, 3.24 times 10 to the negative 4 meters squared, cosine of theta. The value of theta is 0 because here, when we look at this diagram, we can see that B perpendicular is equal to B. Okay, so this gives us theta to be equal to 0 degrees. So here we have theta to be 0 degrees, so cosine of 0 will be the number just 1. Okay, so let's complete this solution. So we have the final magnetic flux, which is 1.62 times 10 to the negative 4 Weber. And very quickly, I'll write the initial, this is a B, the initial magnetic flux is BA cosine theta, but initially the magnetic field is equal to 0. Okay, so if the magnetic field is equal to 0, then the initial value is just 0 Weber. Okay. So therefore, the change of the magnetic flux is 1.62 times 10 to the negative 4 Weber. I'm going to put a box here because we have a final of 1.62 times 10 to the negative 4. Subtract 0, and it's 1.62 times 10 to the negative 4. Okay, now let me squeeze here on the right-hand side the induced EMF. So I'm going to copy the equation again. So I have epsilon is equal to minus n, so the number of turns, the change of the magnetic flux over the change of time. Okay, and I can plug in the values. So here I have EMF is equal to negative 25. The 25 comes from the problem that states that we have 25 turns. And then from my change of flux, I'm going to use this 1.62 times 10 to the negative 4 Weber and divide it by change of time, which the question says it's 0.8 seconds. So let me write that. So I have 1.62 times 10 to the negative 4 Weber divided by 0.800 seconds. Okay. So I have a value of negative 5.06 times 10 to the negative 3 volts. And I'll put a box here. Note that we have a negative induced EMF. Okay, so part B is asking us to find the magnitude and direction of the induced current in the coil while the field is changing. So this is fortunately quite straightforward. We can find for the current by using Ohm's law. So I have current is equal to the change of voltage over R. This is an R, I promise. So you know, voltage over R, which is equal to, again, the change of voltage. We have 5.06 times 10 to the negative 3 volts divided by 0.350 ohms. So then we have 1.45 times 10 to negative 2 amps. Okay. I want to know that this value is the magnitude. As you can see, I kept my values positive because that will be the magnitude of the current. Okay. So to solve for the direction, and to solve for the direction that is the induced direction, let me just write a few bullet points and I'll scroll up. So we have start the problem at t is equal to 0 seconds, and then we are getting another data point which is t is equal to 0.8 seconds. Okay. And the magnetic field increases in the same direction as the normal of the plane. Okay. So this gives us that the flux is positive and increases. Let me scroll up for a second and let's go back to what I wrote at the beginning before we start the problem. So here we have, if the magnetic flux through a loop is becoming more positive, which is the case of our change of flux, then the induced EMF creates a current and associated magnetic field that produces a negative magnetic flux. So the current to create this magnetic field, or due to the magnetic field, think that the current would go counterclockwise, because if you put your thumb in the direction of this coil, then inside the coil, your fingers are going to curl upwards or towards the positive z-axis. Okay, so they're going to curl, think negative z-axis outside of this coils, and they're going to point out in the positive z-axis inside of the coil. And to create a negative response, then, or to get a negative magnetic flux, then your fingers will have to have a direction, or the current will have a direction which is counterclockwise. Because if you have a direction counterclockwise, then the magnetic field will be in the opposite, so the flux would be in the opposite, or a negative flux. So, which I kind of went ahead of myself, but C is what is the direction, clockwise or counterclockwise, of the induced current. So the induced current, which will give a negative flux, is therefore clockwise direction. Okay, so let me scroll up again in this diagram so I can color code it. So the yellow arrows will be the current with the yellow magnetic field, but the direction of the induced current that gives a negative magnetic flux will be this blue arrows, which is the opposite direction, opposing. Blue arrows is clockwise, so therefore direction is clockwise. Okay. All right, so the last topic in this video to do the third question is self-inductance. All right, so self-inductance will be the following. So the current increases with time, and the magnetic flux through the loop due to this current will also increase. Okay, so the currents will increase, and the magnetic flux will also increase. The increasing flux, so this flux here from the first sentence, will induce an EMF, which is the example we just did, example number 2. Okay, the increasing flux gave us an induced EMF, which we calculated, and in the circuit, and this opposes the change in the magnetic flux. So this EMF will go against the change of the magnetic flux, which is the part B and C in the question we just completed. So as the magnitude of the current increases, the rate of increase becomes less and less, and the induced EMF decreases. So in a way, the change of flux through a circuit arises from the circuit itself. Okay, the circuit will give this change of flux by itself, and that is why we call it self-induction. Now, let me put some equations on the screen that will help us solve for different variables with this self-inductance. So now recall Faraday's law, which was this epsilon is equal to the negative n change of flux over change of time. Now, I'm going to introduce the self-induced EMF that is proportional to the rate of change of the current. So here I have my epsilon is equal to a negative L, which L is the inductance measured in Henry's. Capital letter H comes from a scientist. Multiply, so negative L will be multiplied by delta I over delta T, the change in current over change of time. The negative sign, this negative sign here, shows that the change in current induces an EMF in opposition, so opposite direction, to the change. So let me write the units for us to start question number 3. So I have 1 Henry, again, is the unit for inductance, is equal to 1 volt times second over ampere. And I have that N, number of turns, change of flux divided by change of time is equal to L, change of current over change of time. I cancel the negative signs because there's a negative signs on the left-hand side, there's a negative signs on the right-hand side, and that's how they cancel. So I can rearrange this equation and solve for inductance in both sides. So I can have L is N change of flux over change of I, because the T cancel, yes. So when I put a delta T or delta T, they cancel. And I can have this as N magnetic flux over I. Okay. So the inductance of a common solenoid. So remember, a solenoid will have N turns. A solenoid is going to have a length, and the solenoid will have a radius. And we wrote in the previous chapter the lowercase n to be the turns per unit length, which is capital N, number of turns, divided by L, the length. And I'll redefine the magnetic field again from our previous section, which we had mu naught N over I. Okay, let me scroll up a little bit so we can recall what this lowercase n is. So I can write this as mu naught and then substitute lowercase n and write uppercase N over L, turns per unit length, times current I. Now this B, I'm going to introduce this into the equation for magnetic flux. So I'm going to write the magnetic flux. Okay, I'm gonna write the maximum so that way I don't have to put the cosine component. So the maximum magnetic flux is equal to BA, which is equal to mu naught N over L I, and then I have this value of A. Okay, which again, A is the cross-sectional area of the solenoid right here. A is equal to cross-sectional area of solenoid. Okay, so plug in this back to the inductance. I can have that the inductance is equal to N flux over I, which is equal to mu naught N, and N gives me a squared, A over L, there's I will cancel. And here I'll write again the turns per unit length. So here we call again that we have uppercase N is lowercase n times L, or N is equal to uppercase N over L. Okay, number turns per unit length. Okay, I'll write it again so we can have it all on screen. And so combining all this together, we have that L is equal to mu naught N L quantity squared times the cross-sectional area over the length, which can be mu naught N lowercase n A times L. And here a area times a length, area length, that's what we call a volume. So this is equal to mu naught N squared times a volume. Okay, so let me put this in red here, brackets. Okay, so we have different ways to solve for L, okay, the inductance, and we have different variables. So we can write it in terms of a volume. Then we can have, mu naught would be a constant for our case. And then if you have the physical dimensions of your solenoid and you have the turns per unit length, then you can solve for the inductance of the common solenoid. So the third question will be to find the inductance, self-inductance, EMF, and solenoids of this question. So calculate the inductance. Let me scroll down. Might be helpful. Calculate the inductance of a solenoid containing 300 turns if the length of the solenoid is 25 centimeters and its cross-sectional area is 4 times 10 to the negative 4 meters squared. And I wrote the equation, so I started. We have L is equal to mu naught N squared times area over length. So it's the first question on the left side because we have these variables straight away. So let's solve this. So I think it'll fit 4 pi times 10 to the negative 7 meters. I forgot the Tesla meter ampere. So we have 300 turns, correct? So we have 300 turns. Quantity squared times 4.00 times 10 to the negative 4 meters squared for the cross-sectional area divided by L, 25 times 10 to the negative 2 meters. I forgot a 0.0 here for correct number sig figs. All right, so we have L to be 1.81 times 10 to the negative 4 Tesla meter squared over ampere. And I want to make just a point here that Tesla times meter squared over ampere, this is the unit of Henry. That's an R. So this solution can be written as 0.181 millihenry. Okay, so part A is calculate successfully. B is calculate the self-induced EMF in the solenoid described from part A if the current of the solenoid now decreases at a rate of 50 amps per second. So there's a constant rate of decrease. So if the rate decreases at 50 amps per second, there's no problem. So you can find that epsilon, self-induced EMF, is equal to the negative L change of I over change of T. And note that this 50 is change of I over change of T. So this is equal to negative 1.81 times 10 to the negative 4 Henry multiplied by 50 amps per second. And here I want to note something that we have the rate which is decreasing. Okay, so if I have a decreasing, I'm going to put a negative sign here because it will be decreasing. If it's just said increasing, I would have left it as 50 or positive 50. And the solution is 9.05 millivolts. So those are three examples, one of the magnetic flux, then we applied Faraday and Lenz's law, and a self-inductance of a solenoid in question number 3. Okay, 3 easy questions to test these concepts. I will put the information for RL circuits, so circuits with a resistor and inductor, large inductance, in a separate video so we can complete examples 4 and 5 of lecture worksheet 6.